Example 14.5 says find the zeros of the polynomial function given and state the multiplicity for each zero. Write the function's equation as a product of linear factors. So the phrase here, product of linear factors, is a new phrase, but it's actually something that we've done prior. I made mention that some of the factoring we did in an earlier section, and also earlier in this section, was called a linear factorization. So this is just another way of asking you to make sure that you have a linear factorization. Now before, we weren't actually trying to make a linear factorization, we were just observing that the factorings that we had in some cases was a linear factorization. But here it's saying we absolutely have to make sure that we get a linear factorization. So we will do that as a byproduct of trying to find the zeros. So when we see the phrase find the zeros, this means that we are going to end up setting f of x equal to 0. But the only way that it's going to actually be beneficial for us is if we can get f of x into a factored form. So that's actually the first thing that I will try to do, is perform some kind of factoring on this. So the initial technique that I would try is factoring by grouping. And since there's 4 terms here, it is actually the only technique that I can try from a traditional factoring technique perspective. So if I was to try to do factoring by grouping, first group I could factor out an x squared, so I'd have x squared times x minus 2. And then from the second group, there's not really a whole lot to take out here, so I'm gonna force a -1 to be taken out. So then I would have -1 times 11x minus 12, and they would look like that. And because none of the factors in x squared times x minus 2 match any of the factors in 1 times 11x minus 12, the factoring is going to break down. You're not going to be able to take this technique any further. So in other words, factoring by grouping fails. And we have not yet seen a great deal of factoring by grouping fail for us. We've always been able to try factoring by grouping and make it work. So this is going to be something that has to be addressed. And this doesn't mean that we're just going to stop the problem. It means that we have to find another way to get the factoring done. Otherwise, setting f of x equal to 0 is going to be pointless. We have to get the factoring done. So the way that we get the factoring done is by the factor theorem. So for the factor theorem to work, we need to also use the remainder theorem, which says we're going to take the equation that we're trying to factor, we're going to treat it as the dividend of a division problem, and then we're going to use x minus c to represent the divisor. This is all in the remainder theorem and factor theorem from back in section 13. Now the problem here is that I don't know a value of c. In section 13, I always provided you with the value of c. Here I don't. So the p over q list that we were coming up with in the examples 14.4 that the rational zero theorem gives us, that is the list that we want to use to test out for c. So normally c can be any real number that we want, but any real number, there's a lot of options with that, and I certainly don't want to have you sitting here thinking about all the different possible real numbers. I'd rather you have a much more concentrated list to choose from. So I am going to give you the p over q list for this. If you need help with looking at how to create that p over q list, then you need to go back and look at example 14.4. I'm just going to give you that result here. It is going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. I would encourage you to pause the video and calculate that for yourself to verify that this is in fact the correct P over Q list. So continuing on with this list, we are expected to pick one of these and try it out as C. And I'm going to use synthetic division to test it out. So the synthetic division setup starts with the dividend and the coefficients 1, -2, -11, and 12. We are always expected to bring down the leading coefficient from the dividend, and then we're going to pick something to test out here. So I'm going to say let's test out 2. So from that list, positive 2 is there, and I'm going to run through the synthetic division process. So we'll get 2 here, 0 there, 0, -11, -22, and then -10. And remember that the answer line here is the quotient and the remainder. So the remainder tells us what the answer is to f of 2. That's what the remainder theorem tells us. So f of 2 would be equal to -10. Now, in order for the factor theorem to apply correctly, we need the answer to be 0. In other words, the remainder has to be 0 in order for the factor theorem to actually apply. So this tells me that 2 was not the correct choice. So let's try something else. Let's try, let's try 4. So if we try 4, the initial setup is the same because you're not changing the dividend. All you're changing is your divisor. So we bring down the 1, and we're going to test out 4. So let's see, we'll have 4, +2, +8, -3, -12, and what we're looking for, 0. So again, we have a quotient, we have the remainder, and the remainder theorem tells us that f of 4 must be equal to 0. That's what we're looking for. So what does the factor theorem say that we can do with this? Well, the factor theorem says that we can now take f of x and we can factor it as the divisor times the quotient. You can only do that if the remainder from that division is 0. So f of x is going to be equal to x minus 4. Since we were using 4 for the divisor, we just substitute in 4 for c, so that's where we get x minus 4, and then the quotient is going to be coming directly from the quotient portion of the division, which remember is going to be a constant, and then an x coefficient, and then the x squared coefficient. So that's going to give us x squared plus 2x minus 3. So where factoring by grouping fails, the factor theorem prevails. It gives us an initial factoring step that we could not get accomplished with a traditional factoring technique like grouping. So now I want to look at what we have and see, could I go back to using a traditional factoring technique, say for example trinomial factoring. We can apply trinomial factoring to the quotient, and we're going to end up with x plus 3 times x minus 1, and that would be as far as I could take this factoring. And I want you to notice that the degree of each one of these factors is 1, which means that each one of these factors is a linear factor. So just because of the process of finding the zeros, we were able to come up with the linear factorization. So I'm going to go ahead and box that in, and I'll make a note here that this represents our linear factorization. So once we get to the point where we've done as much factoring as we possibly can, then I want to actually find the zeros. So all of this is just leading up to letting f of x be equal to 0, which is what we're really supposed to be doing here with this problem, after the linear factorization, of course. So now we would say 0 is equal to x minus 4, or 0 is equal to x plus 3, or 0 is equal to x minus 1. So that would give us 3 answers: x equals 4, x equals negative 3, and x equals positive 1. And each one of those comes from a linear factor, so therefore they all have multiplicity of 1. And we will box that in, as it is the zeros of the polynomial function along with the multiplicity, and then we've already boxed in our linear factorization.